Welcome to the Industrial IoT Spotlight, your number one spot for insight from industrial IoT thought leaders who are transforming businesses today. With your host, Eric Walenza.
Welcome back to the Industrial IoT Spotlight podcast. I'm your host, Eric Walenza, CEO of IoT One, and our guest today is Troy Harvey, CEO of PassiveLogic. PassiveLogic has built the first fully autonomous platform for managing the whole building lifecycle. In this talk, we discussed PassiveLogic's approach to applying edge computing based on their Hive controller and swarm sensors, and we also explored the application of deep physics models to build a digital twin foundation for building operations optimization. If you find these conversations valuable, please leave us a comment and a 5-star review. And if you'd like to share your company's story or recommend a speaker, please email us at team@iot1.com. Thank you. Troy, thank you for joining us today.
Absolutely. I'm glad to be here.
So Troy, I'm really interested in your company. I love talking to CEOs of companies that have a deep focus. A lot of companies, technology or industrial IoT companies, are building something that is horizontal enough where, especially younger companies have a little bit trouble determining who are we serving, right? It's kind of like our technology can serve multiple markets. And in your case, it's crystal clear. So I'm really looking forward to learning who you're working with, how you're, what types of problems you're solving, and then the tech stack behind that. But before we get into that detail, I think you have personally a very interesting background. So I'd love to learn a little bit more around what you were doing before you set up PassiveLogic, in particular at Heliocentric, because it looks like this kind of directly led into the logic behind PassiveLogic. And then why did you make a jump? You were already CEO of Heliocentric. What caused you then to, I don't know if you sold that or if you moved on from that organization and then set up PassiveLogic in 2016?
Yeah. So, what we really built at Heliocentric was a lot of expertise in the early 2000s around building simulation and building physics. And what we recognized at the time about buildings was, for hundreds, if not thousands of years, architects and builders of buildings had always sort of designed buildings and then just built them. And as an electrical engineer, this is sort of a crazy idea because in most other kinds of engineering, you always beta test things before you make the real one. And so what we really built was a lot of expertise around simulating virtual buildings, the virtual people inside those buildings and the virtual systems, so that we could work with architects and developers and engineers around how do they build a better building and take that, their concepts and build, different kinds of walls and different kinds of materials and different kind of HVAC systems and reshaping the buildings in ways that we could get the outcome we wanted going through hundreds of variations of a building. And then we had a lot of guarantees around now we can go build that and have some certainty around how that building will operate and work. And so that's really where, Heliocentric sort of developed its skill set. And I think a lot of the rest of the industry, what we found was that you could design really great buildings, but as we found through the LEED process, when they hit the ground, they rarely lived up to their expectations. Even if they were great engineering, good installation, well engineered and tweaked and tuned and commissioned in all the ways. And so I think we got involved through a Department of Energy contract to start looking at these buildings. And we recognized that the real core challenge in buildings was something that maybe the rest of the building industry hadn't kind of come to grips with, which was buildings are the world's most complex systems. They're effectively these huge, giant stationary robots, but with a level of inputs and outputs, sensors and control points, or what we call degrees of freedom in robotics that's out of the scale of anything else people make. And that scale of problem just wasn't solvable with the tools that we were given to go make buildings work. And this is sort of the fundamental underlying challenges of buildings. So right about that time, I met my co-founder who hired my company to help him build a really cool house. And he had just come out of, an IPO for his previous company called Fusion. So Fusion.io really innovated, and he was this founding engineer that came up with all the core technology of these flash drives that we all use today. So before that, there were flash chips, there were hard drives, but nobody had figured out how to use commodity flash chips in a really durable way, really, really fast, and made these, these million times faster hard drives. And that's what Fusion.io did. They had a really successful IPO, and they were selling themselves to SanDisk at the time. And he was building this house, and he hired my firm, and he's like, "Where's all the good controls? Where's the good automation platforms?" And I was like, "Well, you're looking at all of it." And he's like, "Wow, this stuff's garbage. Like, how could this be like 2016?" And so I started showing him what we were working on, and he came on as an investor in that. And then within a couple of months, he was like, "Wow, this is just so much more interesting than Fusion.io ever was. I'd like to, come on as a co-founder, and let's go build this company." So that's really the starting of PassiveLogic 4 years ago.
And I guess there's two big, you mentioned kind of two big tracks here. So one is when you have a better understanding of how this complex asset will function, you can identify potential issues, you can optimize efficiencies and so forth. So there's this kind of optimization angle and this sense check aspect. And then there's also potentially an innovation, because I imagine the status quo is people tend to be conservative. If you're just going to build this complex asset and you can't really test it in advance, you're probably going to do what you've done before. I imagine now if you can really do some deep kind of digital twin, you have a lot more flexibility around testing out new concepts and more confidence that they might actually work in the real world.
And I think even what Heliocentric was doing in terms of, let's help the design and engineering process on buildings, make buildings better. Even with that, what we found and what the rest of the industry does is that's sort of the end of the road, right? You can design and engineer things, but whatever you come up with, once it hits the ground, once it starts getting built, those are just paper, right? That's paper in the field held by somebody else who is then expected to implement it. And so one of the big challenges was what we design, what we make, or what we think about, or how we engineer buildings or other systems. They hit the end of our CAD system, they go out our printer, and that's the end of the road, right? And so there's no connectivity as to that intent, that engineering or design or architectural intent transferring to the next step of the process. How do we build and create digital work sites and operate and maintain and manage those same assets?
Okay, so if we go now a bit deeper into the business itself, I suppose it's all fairly clear to listeners that the market here is buildings. Is this primarily commercial buildings? Are you covering industrial, residential? What's the 80% rule right now? Yeah,
so our core market is really commercial buildings and industrial buildings, but that includes multifamily residential. Many of our investors are multifamily residential REITs. But more broadly, what we're doing will apply to process control in industrial settings. So there's kind of a big umbrella, but you could say the sort of outer skin of that umbrella is what happens in buildings.
Gotcha. And then there's a lot of challenges along the life cycle of a building, right? So where do you tend to be involved? Are you full life cycle? Are you more in the planning phase, in the operations phase?
So we're full life cycle, and that's one of the core values of PassiveLogic, is that what you do at the design side is really all you have to do, and then that lives through the life cycle of that building. But for our marketplace, really you can pick up PassiveLogic without dependencies at any stage of the building's life cycle. So whether you're pre-design or early design, or you're in construction and you want to apply automation to buildings, or you're doing retrofits and you're thinking about how do you maintain and manage buildings on that end of the spectrum. So one of the core values, and backing up, I think more broadly, to understand buildings as these robots, right? These big complex robots. The framework to understand PassiveLogic as an autonomous platform for buildings, and if you if you look at, how autonomous systems change the way we think about, say, vehicles, we think autonomous technology applied to buildings has far bigger, far deeper ranging implications than it ever had for vehicles, with larger economic and systems integration impact. So you look at buildings, for instance, and in the first world, buildings are twice almost the energy impact of vehicles. The costs of integration, the footprint of these systems, and the economies around them is far bigger than anything else. And so in simple terms, you can think of PassiveLogic as, what if you took the brain from an autonomous vehicle and taught it not about driving, but taught it about buildings and building systems and the underlying physics and how to operate all those things as a whole unified, complete system.
Gotcha. So you're there's been BMS systems around for decades, but the BMS systems were not intelligent in terms of decision making, right? They were kind of platforms for visualizing. And so can we view PassiveLogic kind of as a next generation BMS system that now has this AI capacity built in to make better decisions?
Yeah, I think that's broadly what you can think of. You can think of as that BMS, or what we would say more broadly, control, because this is the fundamental of every building. You need a control system. This is really a requirement, right, to make a building go. And whether that's at the quote unquote high end of BMS or at the low end, just simple controllers, what we've seen over time is this evolution. So the big automation companies today, they all came out of the 1850s with the breakthrough innovation of the mercury switch thermostat. That was the beginning of the controls industry. And what we saw is the evolution of that went from thermostats to fixed function controllers to the PID control loop to these BMS control systems or digital control systems in the 80s. But largely what we have today is virtually no different than what we had in the 1800s. It is just digitized and given some tooling around how do we organize lots of thermostatic control or lots of PID control in a unified box. But that box, the context is really like 1970s or 1980s style programming. And you could go through a series of proofs in terms of computer science. You could say, well, given the complexity of a building, how many different if-then-elses, for instance, would I have to write? And you would find that it would take, 100 engineers, thousands of years to ever write a complete set of if-then-elses for any given building. And so this is that underlying challenge, right? So where the end of the road was for BMS and why we're not getting to where we need to is that it's really quite the end outcome of where we started in controls in the 1800s. And we're just ready as an industry to say, okay, what does that new foundation look like? What does that new path look like? Because we're out of steam on the old path.
Okay, fascinating. As you're speaking, I'm looking at one of the videos on that's kind of visualizing how you would use this in a complete building to visualize the skin, or the operations under the skin of the building. So, and what I'm thinking here is that you have, maybe we can go into this now, who are the buyers and who are the end users? Because you have this product that is managing an extremely complex asset that's being passed from hand to hand, right? So there's the architectures, the developers, the construction team, then there's the building operations, there's maintenance. And my feeling here is that the tool has functionality for quite a range of different users. And also through the life cycle, there might even be different buyers. So I'm also curious who would, I guess the building owner might be the buyer here, but can you share a little bit, who are the key stakeholders here? And then how does this evolve over the life cycle of the construction?
So, as you're talking very tangibly to our Autonomy Studio software, which allows somebody to design their own autonomous system for their building. We can talk about why that is and why that's important. But yeah, there's a sophisticated value chain in buildings. And one of the things that PassiveLogic does is really address problems along that whole path for any one of those value chain stakeholders. But what we focus on the most And I think this is rare in what we see today in the IoT and AI and the buildings control industry is we focus on who is the fundamental customer. And generally speaking, that is a installer of automation equipment or an HVAC installer who more broadly is typically the organization who's doing control in buildings. They're kind of the de facto control user because they have to control their systems. And we focused on building a user experience around the workflow of how buildings actually go together and how those installers have to interact with that whole business process from getting a project to getting in and out of the building. And so core to that viewpoint is that one of the things that PassiveLogic's been able to do is while we provide all these value adds, whether that's on the maintenance side or the energy side or the analytics and insight side, we decided as a company really not to monetize those things. We decided to give away those as a side effect of the core need, control, and really sell our control platform at a competitive price to what you could buy in the market, but then make our platform really scale from the little coffee shop on the corner up to a skyscraper level and make the pricing work across that band. And that's another thing that's really unique about how we are handling technology. I think often in industrial systems that we see is these kind of old crufty systems that just aren't really good in the first place, but they're the flagship of the automation provider. And then they try to hit a lower end market. And what do? They take an old crufty system and they cut half the features out or 90% of the features. And then you've got a cruftier system and nobody really wants to buy it. And so when we look at, say, mobile phones, you don't get a different iPhone than the CEO of Apple. He doesn't get a better one. You all can buy the same one, right? And so PassiveLogic has the same theory about buildings and the buildingscape is that we need to have the same scale, the same technologies, these new advanced technologies for every building, not segmenting the market unnecessarily. So we really focus on that installer base, the contractor base, and build a user experience and this workflow around how their businesses work. And that's really our sell into the market. And then we give away the rest.
So let's see, a contractor base, then that's going to be I don't know, is this, I guess, depending on the project, 6 months to 24 months time period? Is this like a SaaS-based solution, pay per period of time, or and then based on the building size or the number of users on the contractor side? What would that look like from a business standpoint?
No, and this is another differentiator or how PassiveLogic really thinks about the market. So first, we really think that one, investors love SaaS, right? It's an investor-driven decision point to drive companies towards a SaaS model. Customers generally don't like SaaS. And in this market, when you're talking about core infrastructure, and you're saying to somebody, well, pay my monthly bill or else your building doesn't work, that's not a really strong position to enter a market. And you'll probably lose 90% of the marketplace right at the front door. So one of the core concept here is when we say autonomous system, we really mean that. This is an autonomous system, all the AI, all the decision making, it's in your building. When you buy our controls, when you set up our software and you put it in there, it's yours, it's in your building, and that's a core infrastructural technology platform for your building. That doesn't mean that we don't have some SaaS services, but they're opt-in. So those SaaS services are along the lines of, how do I manage my portfolio? Or how do I get remote access to my buildings? These are natural places to have the cloud intersection where you say, well, from my office, I want to access all my buildings. Now we're not like artificially forcing things into the cloud just to lock them up for the customer. So this is core to how we think about markets, how we think about how this market's structured and working within its structure.
Gotcha, makes sense. And that means, I suppose, that the software is running on servers in the building, or is there also, even if it's owned, is it also deployed on a cloud, or what would that look like?
When we talk about autonomous system, the core product is our Hive controllers, and this is a control system that provides really about what is a dozen products, today that you have to integrate in one box that you can install in the building. It does all the control. It goes through all the, control engine, physics engine decision making right in that box, and it provides the interfaces to all your IoT devices, all your sensor devices, all these controllable devices in a single box without having to do any integration. So again, back to the mobile phone analogy, why did the iPhone outsell in 4 years all of computers, desktop computers, in 40 years? And we think there's a lot of reasons for that, but one of the key reasons is pre-integration. So in this market, in the IoT and building automation space, we generally call the installers integrators because that's the core of their work. And we think this isn't what people should be doing with their time. They should buy things that just work, and they should spend their time, designing, installing, and getting new jobs. And so that control system has inside of it, it's not a server, it's got high performance processors right in the control system that when you plug in one of them, even if it's in a coffee shop, it's doing all the decision making right on that control box.
I suppose there's going to be significant differences in requirements between a coffee shop and a skyscraper. So is it just you have your the Hive controller, and then based on the requirements of the building, they might require one or more? Is that it?
So that's part of it. So part of the integration story is that the AI, the underlying technology, the software enabled us to then really integrate the hardware, make the hardware very software defined. And this allowed us to replace what is today a catalog of different controllers and automation devices, nodes and network devices into one box. And then it really becomes a question of, if you're in a coffee shop, do you need one? And if you're in a skyscraper, maybe you need hundreds of them throughout the building, each one of them doing their own role. But when you daisy chain them together, when you connect them together in a network, they work out those roles together in a swarm computing cluster. And they are both taking care of their own jobs as far as I/O, talking to sensors, talking to IoT devices, talking to controllables. But then all of their capacity, all their compute capacity gets shared across that whole network. And so as your building gets bigger, you have more controllers, you have more compute capacity right there in the building.
Very interesting. Very interesting. Okay. Yeah, we've been doing a fair amount of work into edge computing lately. And it's a topic that's very high interest right now, but still relatively early stage. But this seems like a very practical approach to enabling fairly sophisticated edge computing, because this topic of how to do deep learning outside of the cloud is still a challenge. But it sounds like you've found a practical solution here. Where is the business today? So I know you just raised 16 million and you're kind of coming out of stealth mode. Are you already selling into the market? Are I imagine you've already done some projects, but are those more pilot projects, or do you already have kind of a commercial product out there that's scaling?
Right now, we've had private pilots out in the field for 2 years with a variety of different systems, a lot of different complexity that were managed, that we were brought into those projects to make go. We just raised this $16 million Series A. And then, fun to see that the both top tier lead investors, as well as a lot of strategics from a variety of different building points of view. And we're going to be unrolling our private pilots with some strategics over the next few months. And you'll see us go to general markets, to the rest of market next year, about summer next year.
Great. Oh, super excited. Are you able to share any of the investors, or do they prefer to not be?
Sure. Yeah. So our lead investors were the investor Addition and Keyframe. We were actually Addition's first investment in their new fund, which was the second largest debut fund of all time. In our strategics, we have strategics from both the US market and European market, both building owners on the commercial and multifamily residential, as well as HVAC manufacturers components, one of which is based in Switzerland. So there's a wide variety, and we ended up actually that investment raise was about 3 times oversubscribed. So there was quite a lot of other investors that we really wanted to invite in, but we really ran out of room for collaboration at this point. But we'll see more of that as we get into next year and get into our next raise and can really offer more room for more strategics within our next round.
Yeah, well, it's a good problem to have. But this is one of the most interesting technology trends right now is these industries that have not evolved so much in the past, really the past several decades. Now, all of a sudden, having the opportunity to adopt best-in-class communications and computing technology. So I can see why there'd be a lot of interest there. Why don't we go now into the tech stack a little bit? So you have your server, and then behind that you have management platform and this deep learning or this AI solution. Can you just? We've already talked about a couple of things that you're doing, but could you just give us kind of the tech stack walkthrough? What is the hardware, software, and also if there's any services that you're also providing there, just the full perspective here.
Yeah, absolutely. So you brought up this notion of edge and edge AI in particular. And so we think, PassiveLogic, not just in this industry, but when we look across multiple industries, is really leading what that notion of edge-based AI looks like. And I think you probably are certainly aware why this is super important, right? There are just certain things you could never do from the cloud, not from a point of durability or resiliency, right? When we think about autonomous vehicles, at the speed of light, when you see that you have to brake from your vision system because you're going to hit a crowd of people and you go up the server and back down, you've traveled 40 feet and you're going to run into that crowd of people. It just can't be done from the cloud by speed, but also by resiliency, right? What happens if you lose for 100 milliseconds your connection? This happens all the time. Well, building systems aren't quite as fast as that. We're generally not driving our systems as quickly as that. But it's the same problems, right? We can't really do things from the cloud in real time in the way that you need to do for some of the real-time AI. So our AI system is in the building. It is in each controller. As you spread those controllers around, they're working together as a swarm team. Now, a couple of things that are really unique here is we're built on what we call deep digital twins. So you may have heard this notion of digital twins in the industry, and usually what people mean is something very thin. They mean, it's CAD, or what we call in the buildings industry, BIM, 3D CAD with, names on everything, and maybe you can attach a sensor point to it. That's not all that useful, right? Like there's a lot of, I think, companies looking for a value point in this idea. It's a solution in search of a problem. But when we talk about deep digital twins that are core to what PassiveLogic does, we're talking about the digital twins are the AI. And this is a really important notion because if you're doing building systems or you're doing campus systems or you're doing energy systems or maybe you're doing process control, the thing that's different about this from autonomous vehicles is that every building, every system is completely different. There's no two buildings that are exactly the same. Whereas if I'm Tesla, I can train 10 million miles of test track, and then I can train up a neural net, and then I can sell that to 100,000 people. And it's not learning anymore, right? It's a static model for 100,000 people, exactly the same. But in buildings and systems, process control, we need something where the average user can define their own AI system, their own autonomous platform for their own unique building, unique architecture, unique system topologies, and so forth. And so at the core of what we enable is, instead of programming, and we've already kind of established that's somewhat of an impossibility with conventional means, how to control these systems very well, we give people an environment where they can draw what a building looks like. They can draw what their systems look like, drag and drop different components, pumps and fans and valves and boilers and movable robots that move like shelves around with boxes inside of a warehouse that might be like an Amazon logistics center or whatever those componentry are. And those individual components that they drag and drop are these digital twins that understand their own physics. So giving a pump a notion of what a pump fundamentally is. And then a number of things become possible. First, when people draw their system, what they're actually drawing is their AI topology but it just looks like a simple drawing to them of their system. So we translate it into the world they know, and then we get a system topology that meets their building. The next thing that digital twins enable is this new kind of AI called deep physics. And we can talk a little bit more about that, but basically deep physics gets rid of all this training time that we have in deep learning and allows you to draw what your system looks like and start controlling it right away without, millions and millions of pieces of training data. And then it learns right in your building about your building and its behavior. And that, again, is unique for most AI systems. Most AI systems have been learned and they're given to you statically. And so this AI, this digital twin then has another face, which is how do we talk to all these IoT devices? How do we talk to all these protocols? And the one thing I know about protocols is people keep on making more. And so the challenge today is being able to bring those together in some kind of structured meaning about the whole building, all the systems together that anybody can query. And these digital twins provide that structure. And they enable something that we call semantic lowering. When you understand your physics, this is the most meta thing you can know about yourself. So if you're a pump, understanding what a pump does and what it does in a system, and knowing that I want to turn on a pump in physics terms is more meta than saying I want to turn a pump on in BACnet or KNX or LON or Modbus or whatever it might be. And that allows me to do what we call semantic lowering, to take that meta notion of pump turn on in physics and lower it down to a simpler semantic, whether that's BACnet or KNX or English or Chinese. So there's these multiple facets to what these deep digital twins enable. And then the final one is how do you provide a high-level API to all those services that want to plug into buildings? So that's a kind of a big walkthrough on the top level, but I think there's a bunch of those things that we could, go down that tunnel, talk about deep physics or things that grab your attention.
Yeah, I mean, how mature is this technology domain? Are there other applications that maybe our listeners would be familiar with that are already using deep physics in consumer or industrial products?
It's totally new territory. So I'll describe a little bit of the history. Over the last 10 years, most of your listeners are going to know about like the revolution, so to speak, in deep learning. So the question is, what is that revolution really about? And when you ask that question of even AI researchers, usually people say, well, it's about neural nets. But it's not about neural nets. Neural nets have been around since the 1950s. So then what is it about? And the next answer often is, well, it's about CPU and GPU power or the amount of data we have available, right? But it's actually not about those either. Those are maybe, an order of magnitude leg up. But there's something at the bottom of the deep learning stack. When you pull out TensorFlow and you start using training on some data, there's something at the very bottom of that stack of code that makes it all possible. And that's a thing called differentiable programming. And differentiable programming to date has been locked up in the bottom of deep learning libraries. And what differentiable programming is this. Let's take the neural net or the deep learning piece. If I wanted to train a neural net with 1 million neurons in it, prior to differentiable programming, I would have to take, my computer and figure out with some kind of algorithm, some kind of heuristic, how to tweak and tune 1 million parameters for those 1 million neurons to get the right answer for, say, recognizing an image and recognizing that that's a dog or a cat or a horse or a person. And that would have taken hundreds or thousands of years on the world's largest computer to tweak and tune all those variables. And so that made neural nets not possible to tune properly, or not possible to really have enough compute to ever really train them. So what does differentiable programming do? Well, all of the last decades of programming, you put inputs to functions and you get the outputs. Differentiable programming is what if your compiler could start with the outputs and give you the inputs. And this means that you could start with the answer, the one output, and you can reverse the code and get the 1 million inputs. Now, there's a couple more processes to that, but essentially that's that's what differentiable programming does. And it changes what would have taken thousands or thousands of years, turns it into minutes or hours or days. So this core technology had been locked up, and we've been working with Google Brain over the last couple of years on generalized differentiable programming. What if you could write any program and you could run it both forwards and backwards? And then what if you could now build heterogeneous neural nets, which is the library we've been working on at PassiveLogic, where not every neuron's the same, but every neuron's different and every neuron has a specialty. And now you can make those specialties, in our case, physics, but it could be in another case, maybe economic systems or a variety of different industry interests. So with PassiveLogic, what we've been able to do is build these physics networks. They break down, they look a lot like a neural network, but they represent the physics of a pump and a boiler and a fan and a window and the building and humans and human comfort. And you can train them just like you train deep learning. But there's a few really big advantages. The first thing about deep learning to understand, and that's really problematic about deep learning, is when you go through the steps of making a deep learning system, the first step is you have to have the data scientists to figure out how to shape their neural net. The second step is that it knows nothing. That neural net's completely blank, and you have to train it on a ton of data. One, in physics, what are you training on? You're training on stuff that Newton already invented 200 years ago, right? Like why spend 3 years and gobs of data to learn something that we already know? And those two steps are 99% of the work. The last step is optimizing your network. So what this allows us to do is basically build neural networks, these heterogeneous neural networks of physics that are represented by components that when you connect those components together, you're building that network that now you have the structure of the models and you're 99% of the way done. It's already usable. And now you're just in the optimization that can be done locally, and you can do it many orders of magnitude faster than you would do regular deep learning. That's how deep physics works on a top level.
Okay, fascinating. Yeah, this is really the first I've heard about this. So really, really interesting. And you said you're working with Google Brain on this. Is this something that was funded? I forget who you mentioned was funding some government agency before. Did this come out of a kind of a funded research program, or how did you identify this as a potential breakthrough?
Right. So we had been building this autonomous platform at PassiveLogic and identified that you really needed to get this performance speed up that could make it a real-time process. So before PassiveLogic, the next best thing you could find on the market was from the Department of Energy. They have a physics simulator and they have some optimization software, and you can get an answer in a week of all sorts of computer simulations of what the next step would be. But we need an answer in a second. So we started working with the Department of Energy. We've had several contracts with the Department of Energy. They just gave us a follow-on contract to make a standard around these computable deep physics digital twins. The goal there is multifold, right? One, in our systems, we need to make those decisions second by second. What is the next operation in the building? Given all the dynamics, we're solving the whole building as a system. All of the heating, cooling, ventilation, energy systems, internal process control type systems, all as what is the right solution for right now? And basically, we can digitally simulate and optimize that millions of times a second faster than real time. And that allows us to make these, decision by decision right in the building and do it on a relatively modest processor. The digital twin interest to the Department of Energy is once we go beyond the shell of the building, how do we make energy networks that are peer-to-peer and can communicate back and forth, and you can do demand response, and utility providers and energy storage and distributed energy and buildings can all work together in real time. And you need some currency of proof for this. And the digital twin satisfies that currency of proof that all these entities can work in a peer-to-peer way while proving what everybody says is true, and nobody can game the system. That's one of their aspects of their interest.
Okay. Super interesting. So So all of a sudden, I'm going to bring us to what now feels like a much less interesting topic, but I think still ground that we have to cover. So you've already mentioned that data is not really the bottleneck here, but I can imagine that in some circumstances, you still need high quality data in order for these systems to operate. Is it your experience that the buildings already have, in general, sufficient sensor networks and connectivity? Or when you're being deployed in a building, do you have particular requirements or recommendations for the architects or the developers for what is required in order to make proper use of your system?
That really actually segues really well into deep physics, because one of the things that the deep physics network does is it provides automatic data fusion or sensor fusion of the information you have. And it also provides this greater context of this physics-based network that represents all these things that are happening in the building. For example, say I have 100 zones, but only 50 of them have sensors for temperature or humidity or whatever it is. It's going to automatically sensor fuse based around the thermodynamic model of that building what the rest of those rooms' temperatures are. And it can also automatically synthesize the quality of that synthesized information. So it can tell you whether it's 90% or 70%. So that quality can be used internally for learning. It can also be used externally if you're trying to query the building, as if you're a service provider of some sort of service on our app store. But it infills this challenge that we see around IoT devices, which is maybe multifold. First, there's no really site intelligence for IoT devices today. Most IoT devices are going up to private clouds made from the manufacturer of that IoT device. There are middleware solutions where you can go to data pools in the web, but data pools are just data. Data is not all that valuable. What people pay for is action. And so this provides this umbrella that fuses that data together by essentially, if you can imagine, if you had this neural net of all these physics nodes within the outer network or this complete network of the thermodynamics of a building and those systems that are operating, you're basically plugging sensors in to points in that network that would on their own synthesize their own information for what would happen in that node relative to everywhere else in the building. You're plugging in a higher quality of data by saying, I've got this IoT device, I'm going to drag and drop it into this zone. Now that, let's say it's a humidity sensor, that humidity is plugging into that with this higher quality of data based on that sensor's accuracy that then propagates through the network around it. So it ends up solving this really interesting IoT problem as a side effect of how do we control buildings in the first place.
And then the other question here is around integration or interoperability with either legacy or, especially in industrial buildings, there's a set of companies that have built quite profitable businesses on keeping competitors out and kind of owning the stack. Maybe, we can look at the elevator unit potentially, or in an industrial building at different controls. Is this a challenge? Do you have to come up with kind of clever ways to gain access to this data, or is this, for whatever reason, not a challenge?
So we have a domain that we're focusing on right now, which is really these what we say functional systems, the HVAC, the energy systems, lighting systems, those process kind of control type systems. Things like the elevator are places we'll head, but right now are a little bit peripheral to us. We do connect into those systems to say, occupants who are moving around the building, those are corridors of flow that are interesting to us as a system. I think to your point, we see this is somewhat regional. I think the US probably has the most open networks, and there's been a lot of piling on to particularly BACnet. Europe is maybe not as well aligned around a singular set of protocols. There's a little bit more breakup in BACnet, Modbus, and KNX. In Asia, I can't speak to the Chinese market as well as you could, but I know in Japan that, in working with some customers there, that things are a little bit more isolated and they have been more proprietary. But we think that that's actually a big advantage for PassiveLogic because we provide not only this, very deep AI stack, but the thing is, as a user, you don't ever have to care. So it's a democratizing force that we provide this really easy to use software environment that now the engineer or the installer can just sort of bypass those experts who have largely locked up things around proprietary stacks. And then we're providing a lot of connectivity via broad sets of protocols. That's a somewhat endless endeavor, of course. We get a lot of protocol coverage in a few protocols, and we'll be adding to those over time. But one of the advantages we have is those digital twins, their ability to do this semantic lowering that up until now, we've always had to do this like one-to-one mapping from language to language. And this provides a lot of acceleration around that.
Okay, interesting. So just I'm cognizant of the time here. And I think one other thing I'd really like to cover, I mean, we've already discussed a bit who you're working with and so forth, but if you can just give us the path of use for PassiveLogic. So maybe there's a case, one of these pilot cases that comes to mind, and just give us as much detail as possible about who is the buyer, what was the situation, who are the users, and how the use of the system evolved as the building went through construction into operations.
Yeah, I'm going to pick one of our more sophisticated projects because I think it highlights the kinds of challenges that controls often face. So this is a project that's owned by a fellow called, his name is Kurt Ockershausen. He was building out a property there's multiple different buildings, different use cases, residential and some utility buildings on a 100-acre property in southern Utah, right off the national park called Capitol Reef National Park. So it's very isolated. This is one of the more remote parts in the US, and it was all off grid. So this whole property is powered by a solar system with battery storage, generator backup. It also had to maintain all these buildings in a fairly sophisticated way, including heating, cooling, ventilation, air quality, lighting systems, occupancy systems. And one of the more interesting aspects of this project was that this solar system, it had to be used, if you're off grid, whatever power you don't use just doesn't ever go anywhere. The solar panels only generate what's being pulled from those solar panels. And the flip side of that is you don't know how much power potential is in those solar panels until you draw that power. And so what PassiveLogic's controller does is it has this 60-stage electric boiler that goes from 500 watts to 25,000 watts and slowly uses up more and more and more power until it reaches the peak of what that solar system can produce. And then it backs off, and then it draws more and then backs off. And it does what we call peak power tracking of taking the residual energy that's not being used by the property and turning it into heat. And then the question becomes, well, where do you put the heat? And so the system in real time has to figure out, well, should I put it into the building in a radiant floor? The radiant floor has, 500,000 million pounds of concrete. That's a storage system, but you can only do that up until you meet the thermal comfort of the occupants. Should I put it in the domestic hot water, which you might have value, but it has a limit of, maybe 100 gallons? And is that going to be used readily, right? Is somebody going to use that hot water soon, or is it going to wait till tomorrow and it's going to have some heat loss? Or should it put in 2 banked seasonal storage tanks? And so it has these large 5,000 gallon insulated seasonal storage tanks buried in the ground that it can choose to put the heat in those places. But if you're doing it in July, there's going to be a lot of heat loss before you might need it in December. So it's lower value. But if you're using it in January, you might use it later that day. And so all these real-time decisions of where to best optimize the global system between energy use, the storage of energy, the real-time needs of the occupants, the air quality, and so forth. So what we saw in that system, in just like tuning into one of those components, which was a geothermal heat pump, PassiveLogic improved the efficiency of that system 40% over conventional geothermal heat pump operation from a study from the Department of Energy, just in how it could predict what would be used, how comfort will happen for the day, and think ahead about the right control sequence given the day ahead, as it saw in its simulations the best path, the best navigation path for that control from right now to 12 hours from now. And so that's really, tangible case on the energy and consumption and maintenance side of the building. But maybe more important is we saw a 90% reduction in the amount of effort to do passive logic versus a conventional control, just from that programming to the commissioning step of just getting into the building. So there's a win versus conventional control right out of the gate.
Gotcha. Okay. So when you're looking at the ROI, you can say just on the installation cost alone, because I imagine with a lot, yeah.
Just on the installation cost, you want, right? Oh, and by the way, you got 40% energy savings just for better control.
I know with a lot of systems, you look at the software and you make you run an RFP and then you get quotes on the software and you deploy something. And then you find out that the integration cost actually is 3 times, higher than whatever the technology was. And that wasn't part of the initial quotation process, right?
Right. And that's our focus on, that's the real core value. When we talked about autonomous buildings and we look at the autonomous vehicles market and we said, the autonomous vehicles market, and I think, you must struggle with this. We struggle with this, how smart is smart when people talk about smart buildings. And this became kind of a pet peeve of ours because, when people say smart, they really don't mean smart, they mean connected. And so what we realized a year ago is we could largely leverage the autonomous vehicles industry nomenclature from level 0 to level 5 autonomy. And it fits very perfectly with the levels that we see in buildings. Level 0 is manual control. That's cruise control in a car. That's thermostatics in a building. Level 1 is adaptive cruise control. Level 1 in a building is adaptive conventional control systems, where you have AI systems just tweaking conventional dumb systems. Getting to level 5 automation or autonomy in a building is a really good goal and will be the end goal of all systems. We think in buildings there's something far more valuable, which is automating the installation so that you can broaden its usage. And that savings right at the front door of saying, well, you can install PassiveLogic for 1/10 the effort of something conventional. Well, who cares about we all care that you have better energy efficiency, but that no longer becomes a value add, cost equation decision to make. You're making the decision on just getting a building going in the first place.
Very cool. Can you give us, so I know this depends on the building size and so forth, but can you give us kind of a rough estimate for what the cost might look like for maybe a medium-sized building or a couple different situations?
Yeah, so if you're looking at automation today, a BMS system, we price compare right across the board. So if you're looking at a building install and it's like 50,000 euros or $50,000, it's going to be about the same in PassiveLogic. The real distinction is current BMS systems really hit a price floor of about $30,000 to $40,000, and we keep on scaling down to about a $1,500 entry point. So when we talk about that coffee shop on the corner, that $1,500 entry point is where we start. And it scales up based on the complexity of the controllables and the different, sensors and IoT devices, and how many points that you're interfacing with. In general, what we see across the automation market, that works out to around $1 a square foot, or you could think of 10 euros per square meter type of price point, plus and minus 50 cents per square foot. So if you're on big scale projects, your million square foot or 100,000 square meter projects, those projects tend to start getting into the 50 cents a square foot. And smaller ones, go higher. But then we see about average that $1 a square foot throughout the automation industry.
Maybe last question from my side, and then you can also let me know if there's anything else that we missed here. But let's say we're in this coffee shop scenario. So your simplest potential user, what would be the actual, is it feasible for a small town architect to deploy this and get this up and running, and then for the coffee shop, the proprietor to operate the system? What kind of training would be required there?
Yeah, I mean, that's one of our real advantages that we see. So it probably in those buildings not be driven by the architect or the owner. It would often just be driven by the HVAC company. So they get hired to come make that building work, install whatever kind of HVAC system it might be, air systems, radiant systems, whatever. And they've got to put in a control system. And what we really focused on in that user experience is they can, in that coffee shop situation, get from start to finish in our Autonomy Studios software in less than 20 minutes to set up a coffee shop with a full control system that is more value and more detailed than any BMS system you could buy, but a price point that they would have otherwise be putting in thermostats and zone controllers. So that's really our sell to those guys. And then for the owner, they're getting the benefits of that platform being in place. But we're really, making that trade to the HVAC installer who's going to do it instead of something else.
Cool. Troy, is there anything that we're missing here?
No, I think that's a really good conversation. I would like to hit upon this notion of, levels of autonomy. And we're talking about smart buildings. I think people need to be cognizant. What kind of smart building technology are we talking about? Are we talking about a level 0, a level 1, level 2? What are those levels of autonomy that we're discussing? We're seeing smart building, and start to think down the road about that. What a smart building looks like as opposed to a connected building.
Yeah, no, I completely aligned with your point. It always frustrates me when somebody kind of bottlenecks the IoT or IoT concept into connectivity and say, well, connectivity it's critical, right? But by itself, it's not valuable, right? So it's really the system perspective.
That's right. I mean, data is a whole lot less valuable than most people act like it is. And there's this pyramid of value. And we start with data. If you can make information out of it, if you can say structure and digital twins, that's a lot more valuable. But what really customers are buying is action, right? They're buying that their building works or their process control system is running the line properly. Very few people are like, well, give me a bunch of data and I'll figure out what to do with it and see if I can find some action within here.
So Troy, we'll put your website into the show notes, and we have, of course, your contact from the company there. But what's the best way if one of our listeners is interested in getting in touch with PassiveLogic? Is it to go to the website, or do you have a preferred contact point?
Go to the website, and they can find a contact point at the website.
So Troy, thank you so much for the conversation today. Super interesting.
Yeah, absolutely. Thanks, Eric. Good to hear your questions, and thanks for all the thoughtful pathways to go explore on this topic.
Thanks for tuning in to another edition of the Industrial IoT Spotlight. Don't forget to follow us on Twitter at IoT1HQ and to check out our database of case studies on IoT1.com. If you have unique insight or a project deployment story to share, we'd love to feature you on a future edition. Write us at eric.walenza@iot1.com.